All right, here we are talking about significant figures. This is scientific notation, but we're actually not going to do that today. Significant figures tell us where and around calculated values based on measurements. You guys just got done doing a lab. In the lab, you were looking at graduated cylinders with water. You did some measurement with a ruler. And we learned that, first of all, you have to figure out what your major scale is on whatever you're measuring with. Then you find the minor scale, and you have to estimate one additional digit past that. Okay? Here's an example. We have 3 rulers. What's the difference between these rulers? The first ruler has a major scale of 10 and no minor scales. So how certain can we be of what that measurement is? We know it's between 0 and 10, but we do not know what it is. If you look over at the right, Susan's guess of 3 or Maya's guess of 2 are your 2 best answers here, because that you can't be any more certain. You can't be certain if it's 2.5, because 2.5 would mean you'd have to have two different numbers to compare between. And you can't be certain that it's 3.00. It's just not that precise. The second ruler has a major graduation of 10 and a minor graduation of 1s. So we can be certain down to the 1s digit and uncertain, or we can estimate to the tenths. So here, 3.2 that Susan has said, and a 3.1 that Maya has said, and even Jonah at 3.3 would all be correct readings. Tony's reading, 3, needs an additional digit. So he would need to be 3.1, 3.2, something like that. All right, Emily and Dion have become too precise, and they cannot measure to that close. Our third one, we now have a major graduation of 10s, and what's our minor graduation? We have 10 marks in between each of the single marks. So our minor graduation, we have a middle graduation of 1s and a minor graduation of 1/10. So now we can accurately go. We've got the 10s place, the 1s place, 1/10. So now we can accurately go to 1/100th. Susan has said 3.21. That's valid. Maya, 3.20 is valid. Jonah, 3.22 would be fine. Mark needs an additional digit, just like before. Well, actually, it was Tony that needed the additional digit. Emily and Dion still are very precise, and you cannot read it that precisely. Now, same thing with balances. Here, we have a basic balance. We have a good balance. We have what's called a balance pro, and we have an exacto balance. Same rock on all 4 balances. When we read it on the first one, we read it that it's 100 grams. The second one says it's 140. The third one says 143. The last one, 143.0. Now, remember we talked about being able to read to the most precise scale. Here, our most precise, our estimated value is going to be 0.0. So this exacto balance is accurate to the 1s place. And then it estimates to 0.0 for us. This guy is only going to be accurate to a 1s place. And we know that because the same rock was 100 grams over here, and now we've gone all the way down to 143. This one is accurate to the 10s, and this is accurate to 100s. Okay? So given that information, we look at the balance for this rock. We have a 200 gram rock. But really, it's a 180. Why would 180 come out as 200 on this guy? Because it would round up to 200. It's approximately 200, but really it's 180 grams. And really, if we get more precise down to the 1s digit, it's 177 grams. And if we get precise down to 1/10, it's 177.1. Again, these are all done for you. You're not doing the estimating with a balance. They do the estimations for you. All right, now we have some small pebbles. This first pebble is registering at 0. How can that be? It can't be 0. Well, what that tells us is that this is not a very precise balance. It's not measuring as precise as it could be. The centibalance is measuring, and we've got a 0.02, which means it's accurate to the 1/10th, and then the estimated value is to 1/100th. So this is more precise than this guy. This one, the superbalance, is even more precise. It goes to the 1/1000th. So this balance is the most precise of all. If we round that, though, and just round to one digit, even to 1/10th, those would both round to a 0, which is why this comes out as 0. Same story here. We've got a different rock. This rock is still coming out as a 0. It comes out as 0.02, which is the same as the rock above it. But notice this rock is 4/100ths heavier than the other rock, or 4/1000th heavier. Okay? So again, that estimation's done by the balance, but we can see what we're talking about. So when we say a figure is significant, we're talking about how well it will measure. All right. Because that's what we're going to be using. Now, I'm going to skip that slide and come back to it. First rule when we talk about significant figures in our problems: non-zero numbers always count as significant figures. So in 1457, we have 4 significant figures. But this is not always the case for zeros. Okay? Remember our zeros here. No, here. Was this 0 significant? No, because it's not telling us any information. We got a little more precise here. We got a little more precise here. The superbalance, the most precise, that 0 right there is important. These zeros are not. Okay? These zeros are placeholders. Up here, these zeros not significant. They're placeholders. As we get closer and closer, this is our most significant 0. None of the rest of those zeros are what we term significant. So how does that work? Okay? If you have leading zeros, they don't count. Sandwich zeros in the middle always count. Trailing zeros count with a decimal point. But there's an easier way to remember this. You just have to know your directions. The Atlantic-Pacific rule. Here's the Pacific Ocean over here. Hopefully you all know that. Here's the Atlantic Ocean over here. Okay? This is what you do. If you have a number and a decimal is present, you begin counting from the left. So here's a number that has a decimal present. I'm going to start counting from the left, from the Pacific side. And when I get to my first non-zero number, I will start counting. So I've got 1, 2, 3, 4, 5 significant digits in that. If I had this number, I have a decimal present. I start counting from the left at the first non-zero. Does this one count? No, it's a 0. Does this one count? No. This one does not either. But 3, 5, and then that 0, and that's supposed to be 0, not a 6, does count. So this guy has 3 significant digits. This guy has 5. Okay? If the decimal is absent, then we begin counting from the Atlantic side. Okay? So here's a number with no decimal in it. If I begin to count from the Atlantic side, I can't count that. That's not non-zero. I can't count that. So this guy has 1 significant digit. If I have 203, I come from the right. 1, 2, 3 significant digits. If I have 1500,725,00, so that would be 1,572,500, I start counting at the first non-zero. Is that a non-zero? Nope. Nope. 1, 2, 3, 4, 5. Okay? So, first rule, non-zero is always significant. Second rule, zeros are significant if it's a leading zero and if it's got a decimal, you start counting from the left. If you've got a non-decimal, you start counting from the right. That means you're trailing zeros. Notice here, there's no decimal, so there's only one significant digit. Here's a decimal, now we have 3. Here's a decimal, now we have 4. Our last rule is about exact numbers. If you counted something, there's no estimation. If you have 3 apples, you have 3 apples. So, 3 apples is 3 apples. If you have something that's defined, 1 inch is equal to 2.54 centimeters. That's unlimited significant figures, 2.54. Even though there's 3 there, we don't let that define any of our math. Now, this rule is important when it comes to doing multiplication and division. Okay? The multiplication and division rules are simple. When you add and subtract, the smallest number of decimals is the one that determines the number of significant figures you have. In this problem here, the smallest number of decimal term is 18.0. That's our limiting term. So our answer can only have a 1/10 place answer. And we would round to 1. If we're subtracting, again, this is very precise. This is not precise. We have to go with the less precise number. So we subtract that, and that would round off to 0.06. Multiplication, same story, only this time the smaller significant digits is the limiting number. So here you've got 3 times 2 significant digits, 3 significant digits, 2. You multiply those together. Because there's only 2 here, the most you're going to have in your answer is 2. Here you've got 3, you're dividing it by something that has 3, you've got 4 on the top and 3 on the bottom, so your answer can only have 3. Decimals present, so we're going to start counting from the left. 1, 2, 3. So we'll drop everything past that. Since this next number is a 0, there's no rounding up, so it would be 0.0297. And you can write that in scientific calculation. We will talk about that later. All right, so now you're ready. Thank you very much.